In this session, we're going to continue looking at the definite integral and try and figure out how we can solve a problem like this without using a calculator. So find the area bounded by the curve, which is x squared plus 1, the line x equals 0, x equals 2, and the x-axis. So we've looked at a few ways that we would be able to solve this, including approximation and using the GDC, but how could we actually go on to find it without using a calculator? We're going to look at something called the fundamental theorem of calculus, which connects what we've looked at with definite integration, but also looking at differential calculus. Okay, you remember that when we first looked at differential calculus from first principles, we looked at something called the secant line here between 2 points. We said that we could use this as an approximation for the slope of the tangent. Similarly, when we're looking at integration, we can use the rectangle here, delta x, delta y, as an approximation for the area under the curve. The fundamental theorem of calculus essentially posits that if we have a continuous function on some interval between a and b, and capital F is the antiderivative of the original function between a and b, then what we have is this. The definite integral of the function between a and b is the antiderivative of f between b and a. And what this means is we can calculate f of b, the upper value, and subtract f of a, and that will give us the solution. So this represents the relationship between differential calculus and integral calculus. Going back to the original question at the start of this session, we were asked to, in effect, integrate x squared plus 1 with respect to x between 0 and 2, and we've seen previously how we can use our GDC to just calculate that value to give you an answer of 4.67. Trying to use the fundamental theorem of calculus, let's break this down. So what we want to do is integrate our function, x squared plus 1, between 0 and 2 with respect to x. So how do we do that using the fundamental theorem of calculus? Well, we need to find the antiderivative between a and b. So the antiderivative, so I need to integrate this. If I integrate x squared, x to the 2 plus 1 is x cubed, and then I need to divide that through by 2 plus 1, so I get a third x cubed plus this is going to be x, and I need to integrate that between 0 and 2. So what I'm going to do is calculate f of b, so the upper boundary. So I'm going to do 1/3 of 2, the upper boundary cubed, plus 2, and then subtract 1/3 of 0 cubed, the lower boundary, plus 0. If I do that, I end up with the answer of 4.67 as well. Let's have a look at a graphical representation then of what we're actually doing. So find the area under the curve y equals 3x squared between x equals 1 and x equals 4. So you might want to have a look at that by yourself. We can see here that this area shaded blue is what we're trying to find. So how can we do that using the fundamental theorem of calculus? So the area A is going to be the integral of 3x squared between 1 and 4. So graphically, what the fundamental theorem of calculus says is that if we find the integral, or the area for the upper boundary, which is here 4, and then subtract the lower boundary, so the integral of 1, we will be left with the area that we're interested in here. So we would find 4 cubed, so that's going to be the area to the left of 4, and this is going to be the area to the left of 1. So the difference will represent this. So if it helps to see it graphically, that is one way you can think about it. That gives us the answer of 63. More conventionally, we would just write it like this. The integral of 3x squared between 4 and 1 is the antiderivative of our function, x cubed, between 4 and 1, which is just going to be, we're going to then substitute in the upper boundary, substitute in the lower boundary, and solve to give 63 square units. Similarly then, here another question for you to try. Y equals x squared plus 4 is the curve. Find the area under the curve between x equals 1 and x equals 3. So, again, the conventional route, find the integral of x squared plus 4 between 3 and 1. So the antiderivative is going to be x cubed plus 4x. And we want to find the antiderivative, or the integral between 3 and 1. So substitute the upper boundary in, which gives us this, and then substitute the lower boundary in, complete the maths to give us 16 2/3. Another one here to have a go at. This has got three component parts in the function, but the process is exactly the same. Integrate this function between 4 and 1. So these are each of the antiderivatives, fairly straightforward, and then substitute in the upper boundary. That's what we've done here. Substitute the lower boundary here, subtract, and we end up with an answer of 39 square units. So here are some slightly trickier ones. For each of these, evaluate the definite integral without using a GDC. So evaluate here means give a numerical answer. So have a go at these and then follow through the solutions. Question 1 then. We're going to find the antiderivative of u minus 1 with respect to u. So that's just a half u squared minus u. And then we're going to substitute in for each of these values. So first of all, my upper boundary is 1. I'm going to go through and substitute 1 in for u. And then I'm going to subtract the same thing with negative 2 substituted in. If I do that, I get an answer of negative 9 over 2. Part B then, exactly the same principle. This one draws on some of the other principles from integral calculus in the sense that this is t to the minus 1. So there's a special case here. The antiderivative of this is going to be ln t. However, otherwise it's exactly the same. We're then going to substitute in, so it's ln the upper boundary minus ln the lower boundary, which using the laws of logarithms gives us ln 3 over 2. Part C, you look at the functions next to each other here, you might think there's a cause for the substitution method. However, this isn't the derivative of this. So the simplest thing to do here, first of all then, is just to expand, and then we can take out 4 as a constant. So you end up with x cubed minus x squared with 4 as a constant. Exactly the same process though. Find the antiderivative for this, which is going to be 1/4 x to the power 4 minus 1/3 x to the power 3. We've got 4 out as a constant. We just then need to substitute in for the upper boundary and then subtract once we've substituted in for the lower boundary. So here you can see I'm substituting for the upper boundary for x equals 3, and here I'm substituting for the lower boundary x equals 1. I subtract all that, multiply with a constant of 4, and I get 136 over 3. Some slightly trickier ones again here with e exponents and rational exponents. The first question, part A, we need to find antiderivatives for these, which is going to be a half e to the 2x negative 1 minus 1 over x. We're going to integrate between 5 and 1, so again just substitute in for f of 5 and then subtract f of 1, which gives us an answer of this. So we can do like that or simplify here. Part B, this you can solve by using integration by inspection or using the formula that you may have seen. Either way, this is the integral. We're then going to substitute in for our upper and lower boundary, which I've done here, and subtract, and you end up with an answer of negative 78. Part C, again here, first thing you need to do is convert to rational exponents, so square root is the same as a half, and then exactly as we did previously, integration by inspection, that's going to give you this integral here. So once we've got the integral, again all we're going to substitute in is for the upper and lower boundary, so substitute in for x equals 3, complete this, and then subtract once you substitute in for x equals 0. And once you've done that, here we've just taken out 1 times 2 over 3 times 3 is a constant. Once you do that, you get a solution of 122 over 9. For part D, you may have noticed that this part here, 4x, is the derivative of this. So if we say u equals 2x squared plus 1, du by dx equals 4x. So consequently, we can use the substitution method here. However, it is slightly nuanced. I'm going to substitute in for u equals 2x squared plus 1. So I can rewrite this as u cubed. This I can rewrite as du by dx, and we're integrating that with respect to dx. So these will cancel out, and I'll be integrating u cubed with respect to u. However, before I do so, I need to just convert these, which are in terms of x, in terms of u, if I am consequently going to integrate with respect to u. The way I do that is just take this value of x equals 1 and substitute it into the equation u equals 2x squared plus 1. So u is going to equal 2 times 1, which is 2, plus 1, which is 3. So that's going to be my upper boundary, and similarly I can do the same thing with x equals 0 to give me my lower boundary of 1. I'm going to integrate u cubed with respect to u, which gives me 1 over 4, u to the power 4. And again, substitute in for the upper boundary, which is 3, and the lower boundary, which is 1, and that's going to give me my solution of 20.